Hi Gina, this is Christina. You're gonna listen to me as I pretend I know what I'm doing. Haha, just kidding. I totally know what I'm doing. So we're gonna go from these starting products right here, and we're gonna have a catalytic amount of this sulfuric type acid, and then we're gonna go and form this material right here. We're gonna protect the alcohol group. Now this is important because it reacting with anything over here on this ester, the alcohol is also susceptible to any type of chemistry we might do over here. So it's important that we protect this first. Now in acidic conditions, we need to make sure that anything we form will not be any anions. It will be a positively charged species. So a cation if it is a carbon, etc. So what we're going to do here is first we're going to deprotonate this one right here because it's strongly acidic. So what we're going to do is we're going to take we're going to take this alkene and we're going to use it to deprotonate the sulfuric type acid and put the information right here. Now this one, because it is such a strong acid, it'll be the exception. It will form a negative anion because it is such a strong acid, it'll completely dissociate in this state. So this is the one exception, and we can use this as a base indeed at the end to be able to reform our catalyst. What we do here is we go and we form that here. Now this would form a positive cation right here, a carbocation. So what we're going to do is we're going to actually use the strong formation power that we have for carbon-oxygen double bond and put it right here. So it's going to be at the same time. We're going to use this alkene to come up here, deprotonate that, and then put this here. So the resulting molecule that we have is going to be again still that six-membered ring with the oxygen. However, we're going to put a double bond here and a positive charge here. Now with this situation right here, I make this carbon extremely susceptible to a nucleophilic attack. So we're going to take the lone pair in this oxygen here, we're going to attack it here and push this double bond back up into the oxygen. And the resulting combination of species that we have here, I'm just going to go ahead and draw this group right here as R. So as I go through and draw, we're going to make that group R just for simplicity. So we're going to have R coming up into the alcohol, which has now been adjoined to this six-membered ring. And this is the structure we have here. Now it looks very similar to the structure we need right over here, which is great. We just need to deprotonate here because this also is going to have a positive charge. So we can either take another one of these molecules up here that acts as a base, or we can take the sulfuric acid. I'm going to take the sulfuric acid conjugate base right here, just to make sure we can recreate that catalyst. It's just nice and neat. So we have this lovely business here, and that's going to have an aryl or phenyl group on the outside. And what we're going to do is we're going to use that negative charge species here to come and deprotonate and then put that back here. So what we're going to do is with that we're going to reform this group up here. Again, we're going to have the oxygen lock of its positive charge and this whole six-membered ring attached to protect this oxygen. Because right there that's very stable, and when we do any type of reactivity, that carbon right there is going to be less electrophilic than the one over here. And now what happens is we're going to react this a little bit lower. We're going to react it with two equivalents of a lithium organometallic. Now this had a copper right here would be called a cuprate, and that's going to have a completely different reaction rate. But because it doesn't, the lithium is going to react a little bit more like a Grignard reagent, and the two equivalents is going to be very important. Now this right here is basically the equivalent of a carboanion. So it's going to look more like this, like a carbon with two electrons and a negative, because this organometallic leaves the carbon being very nucleophilic. And so the most nucleophilic atom right here in this molecule is actually going to be that central part of the ester. So what we're going to do is we're going to take the arrow from the bond between the lithium and the carbon, and we're going to squeegee it over here and put it right here, and then pop these electrons up there so we don't have a Texas carbon. Now again, I'm just going to abbreviate this one as R1, not to get confused, and also for ease. What we're going to do is keep that ester in there, kind of. Going to make this an anion, and then have that pop down, and it's going to go attached now to 1. And right here, we're going to have, now the lithium's going away, we're just going to have this species. So it's going to have 1, 2 carbons, and then going into the oxygen, and then to another carbon right there. Now right here, we have to note, because there's an anion here, these conditions are very different. And indeed, when you have an organic metallic, it's a very, very strong base. And so basically you're comparing the potential of having an oxygen anion with a carbon anion, and the stability of an oxygen anion is greater, therefore the carbon anion will not want to stay in solution for very long, and so this will be the more favorable reaction. However, what we're going to notice here is this is what we have our tetrahedral intermediate. We're going to take these lone pair that's on the oxygen, and again use that driving force to create the carbon-oxygen double bond. What we're actually going to form right here is we're going to have, again, that little group there coming in. Here's the R1. That's a 1. We have a double bond oxygen. Actually, excuse me, that's wrong. This is wrong because we were going to do something very terrible. We're keeping this group right here. Again, this driving force is quite strong and quite favorable, and so what it's going to do is it's going to pull it out. And we don't want to create that Texas carbon like I was about to draw, so what you do is you put it out and push it back. So what we get instead of this is we actually get the double bond oxygen. We still have that R1 over here, but what we've now created is we also have this 1, 2, another oxygen, have like more of an ether attached right here. So what we have now is a OCH3 minus, and again that's favorable in the strongly basic conditions. But because we have this right here is it's still a electrophilic carbon, and because there is no copper here, we're going to be able to use another equivalent of that lithium, of the lithium organic metallic, and be able to again draw it from the bond here, come back up, and have it push back up on here, and what we're going to be left with is something that looks a little bit like this. It's going to look a little bit ski-wampus. So just go with me here. It's a little bit hard to draw. 1, 2, oxygen and a little bit. 1, 2, oxygen and another methyl attached right there. And then we have this as a minus. And what we're going to do is we're going to have the H3O plus that was listed as step 2. Very important, it's listed as step 2. So you're going to have that hydrogen there on a very strong acid. And what's going to happen is these electrons are going to come and deprotonate. And what we're going to be left with in the end product, and I'll try to draw the whole thing for you, is we're going to have, so you have the central OH, and then that central carbon, and it's going to be attached over here. 1, 2, that oxygen. This is our buddy from step 1, from that side. And then over here, I'm going to erase this part right here if I could find it. I shan't. So right here, sorry, I got a little ahead of myself. You're going to do you have 2 of them that we added through the organometallic. So you have a 1, maybe, a 1, there you go, a 1, 2, oxygen, another methyl, 1, 2, oxygen, another methyl, and we have this agent right here. Now the last step they want us to do is to take this and to take off this protecting group, because now we have the desired function over here. So to remove this protecting group, what we're going to do is we're also going to use acid. So you're going to do OH3 plus. So I like to draw it like this to skip a step later. And we're going to have water, which will act as this will act as our base, and this will act as our acid. So again, now we're back to extremely strong acidic conditions, and so any anions are going to be inappropriate in this case. Now what we're going to want to do is, in order to get back to the way we had it before as an alcohol, we're going to use the lone pair on this oxygen, and we're going to deprotonate the hydronium ion as such. And again, I'm just going to draw this one as R2 because it gets a little bit long there to draw those. So if we have R2 coming into this with a positive H, or a positive oxygen, there we go, excuse me, have the oxygen here in that 6-membered ring from the protecting group. Now what we're going to do here is we have a good leaving group now, but we need something to balance us out to have a good driving force. Now, interestingly enough, what we're going to do is we're going to take the lone pair on this oxygen, drop it down here to create a double bond, so we make sure this carbon stays satisfied with its electron needs, and pop that back on here. And then what we end up having is, again, that same group. The R2 group was from our original that we just did all the fun jazz from over here. Again, that's the R2. And then we have the OH that's maintained, and then over here what we've created, it's a little bit different than our starting material. But again, it's a 6-membered ring, but we're going to leave it here. Now in solution, at some point, because that is positive, it's possible that there's the hydrogen over here could be taken off, and via elimination something could happen to restore it to the original form. But that's not something that we're really working on right now, and Holly didn't ask for it, but I want to mention it just in case it would have caused me a loss of points if I didn't. But this is how we get the product. We take off that protecting group. Thank you.